Hi, good day. My name is Effi Ofer. I'm from IBM Research, as you can easily tell by my standard IBM suit and tie. We're here to talk today about how to run high-performance workloads using relatively inexpensive object storage. So this is work that we've done in my team really about just a bit over a year ago. My colleagues are Ofer and Ronen Kat, who aren't here today. So the high-performance workload we're going to concentrate on are machine learning, but this really applies to any kind of data analytics. Machine learning is quickly becoming the disruptive technology of the decade. It's happening because of three primary factors. The first one is data, and by data I mean lots and lots of data. There's a report from Forbes that came out in May 2018 claiming that 90% of all the data we have today was generated in the last 12 months. Now, you could argue whether that's true or not, but the fact is that we're generating huge amounts of data on a daily basis. There's something like 500,000 Facebook messages being sent every single minute. There's 500,000 Twitter messages, 500,000 Snapchat pictures, tons and tons of data. Google just announced this week that they have an initiative to provide populace data, basically people movement data to cities. So they're able to collect data from your phones and if you have any kind of mobile computers, identify where you are, where you're moving to, and then sell that data to cities to help them plan. The second factor is accelerators, and by accelerators I mean GPUs, FPGAs, TensorFlow units, and the third one is of course the new algorithms that came out in the last 10-20 years. You could argue that lots of these algorithms go back to the 80s, but there have been some advancements. So in IBM back about 2-3 years ago, we decided to go and make available a service where you can come and do machine learning on the IBM cloud using the IBM resources. IBM will basically provide you with GPU where you're going to be paying for the cycles that you use. So rather than go and spend, GPUs can go up to just a bit over $10,000. You can go and pay just for the cycles that you need. IBM will package the algorithms in an easy-to-use way and give you the ability of storing your data in the IBM cloud. So IBM went and started working on this, and they immediately recognized that with machine learning and deep learning, the data generally resides in POSIX systems, just because that's the most common ways of accessing data. And the data is generally kept locally on the same node where the compute happens. And that happens for performance reasons. You want your data to be close to the compute. The problem with that is that does not scale at all. POSIX does not scale, especially if you're talking about service, handling lots and lots of multi-tenant users. We can get into why POSIX does not scale, but maybe that's a bit beyond the scope. I'll just mention two issues. First, POSIX keeps a state, and the more POSIX connections you have, the slower your system is. The second one is that POSIX generally requires strong consistency, and that has a cost. The second thing to note is that if you keep your data locally, then that's going to cost you. That's because if you need to store more data, then you're going to have to increase your compute as well, because they come together. What you really want to do is you want to disaggregate your data from your compute. So the model of storing the data locally and use POSIX to access the data just wasn't working for a service that was meant to be used by lots of multi-tenant users. And what we came up with is go and store the data in object storage. Now, how many of you had the opportunity to use object storage? Awesome. So quite a few of you have used it before. Just in a few sentences, object storage, unlike file systems where data is stored in files, and block storage where you access data directly through the blocks, data is stored in objects. It's meant to be highly scalable. It's immutable, meaning that you're storing your data, and if you want to update it, then you create a new version of the data and delete the old data. There's no directory hierarchy. It's really sort of it's not really a key value store, but you can think of it that way. You store your data, it gets a name, and that's how you access your data again. So it's really designed for uber scalability. It's designed for high durability. It's designed to be inexpensive. And of course, it's disaggregated, meaning your data resides separate from your compute. So this was perfect. And the IBM team went and started using object storage to put their data in for all of this machine learning workloads. And everything was fantastic until they actually tried it out. And then what they found out is that when they go and they try to run workloads like, for example, image recognition. So image recognition, you got the ImageNet data set, which is probably the most famous image recognition, image data sets, is around, let's say, about 3 terabytes worth of data. Depends on which subsets you take. So what was happening is the data was sitting in this disaggregated storage. Workload was coming in. Data was getting copied into some local storage so it can actually be used by the compute. And it took a few minutes. It took a few minutes just for the data to be copied. So that's when my team got involved. They called us up. We're the research team that's working with storage, scalable storage, meaning primarily storage on the cloud. We work with the IBM Cloud Object Storage, and they asked us for help. And we looked at their system, and it was obvious why it was taking so long. The performance of object storage is really not geared for analytics and high throughput workloads like machine learning. It's meant to be inexpensive, and the latency and throughput for single connections just really is not totally there. There are some numbers here that we benchmarked. You can see object storage is about an order of magnitude slower than a hard drive. It's about 3 order of magnitude slower than RAM. In the rest of this talk, I'm going to describe how we ended up using object storage, however, to provide a high throughput machine learning environment. Just one thing, if you have any questions, go ahead and ask. It's going to be more interesting for all of us. I'm going to try and leave about 5 minutes at the end for questions regardless. So when we approach this, the first question we asked ourselves is, how much throughput do we actually need for machine learning? How much throughput is enough? And if you look at machine learning, the bottleneck is generally your GPU. The GPUs are fairly expensive. They're the ones who do most of the work, especially if you're looking at deep learning systems. And we figured that what we need to do is provide throughput that's sufficient to keep the GPUs 100% busy all the time. Because if the GPUs are not busy, then basically we're losing money. Customers are waiting for the workloads, and we're not getting paid because we get paid by how many cycles they actually end up using. So what kind of throughput do these GPUs actually need? We benchmarked the high-end NVIDIA Volta V100 GPU. We benchmarked it with a number of different workloads. What you have in this table, we're showing here 4 image recognition workloads, ResNet, 2 different types of ResNets, VGG, AlexNet, and we're showing speech recognition, LSTM, long, short-term memory, neural network. This is running with varying number of GPUs from 1 to 8. And what you're really seeing is that With one GPU, we're getting throughput of up to about 250. With 4, we're getting throughput of 570. Let's call it under 600. So this is the throughput we're aiming to achieve. This is the throughput we're aiming to provide. It just so happens that the machines that the deep learning service in IBM was running have up to 4 GPUs. So we aimed for 570 megabytes per second. Just as a side note, if we're looking at the growth rate for CPUs and GPUs, we're seeing 2 vastly different things. This chart here is a chart that I took from a researcher called K-Roop, who have nothing to do with IBM. It's plotting the advancements in CPU speeds over the last 40, close to 50 years. And what we're seeing is that CPUs no longer really follow Moore's law. In terms of the number of transistors they do, in terms of performance increase for single-threaded performance, we're seeing an increase of about 1.1 times. GPUs, however, are advancing very much at Moore's law. We're still getting 1.5 times performance per year, or approximately a fold increase 10 times every 6 years. So one question you can ask yourself is, does that mean we need to support throughputs of, if 570 is our goal today, do we need to support throughputs of above 5,000 in 10 years? The answer is probably not. There's other bottlenecks we're going to hit before that. Maybe they'll get fixed, maybe not. You can already see this today. The move from 4 to 8, there's actually a decrease in performance. That's because of the interconnect limitation, especially with AlexNet. AlexNet is a relatively short neural network. It's a neural network from 2012, if I remember correctly, which in machine learning years is like the dinosaurs. And the interconnect is a bottleneck there. So just as a side note. So this is our architecture for our solution at the 20,000 feet level. I'll get into the details in a few more slides. Really, what we want to do is we want to keep data on inexpensive object storage. So the inexpensive object storage for us, because we're looking at an IBM service, is the IBM Cloud Object Storage. It supports the Amazon S3 interface. From a customer point of view, an object storage is an object storage. We want to support workloads natively without having to change the workloads, meaning we want to support POSIX API. And we want to keep the GPU busy. That means we want to supply data faster than the single connection speeds we're observing. We want to support prefetching and to optimize the traffic. And we want to use some kind of local in-cache memory in order to actually have the compute use that data. So what I'll do for the next few slides is I'll go over each sections, and then I'll show you the final architecture at a lower level. So first question is, how do we end up providing access to data at speeds that are comparable to what GPUs actually need, which we saw was around 570 megabytes per second. The answer is that object storage have a limitation in terms of their latency and throughput when it comes to single connection. Single connections are limited. We're somewhere around 40, 60 megabytes per second or so. But the object storage itself can very easily saturate your network bandwidth if you use it correctly. Object storage, you can think of it, especially object storage on the cloud, you can think of it as this infinite amount of storage using infinite, or from your point of view, infinite number of disks. It supports extremely high concurrency. So really all you need to do in order to saturate your network is run multiple connections. So we took advantage of open source product called S3FS. S3FS is a fuse, meaning a file system running in user space that supports S3 API. It supports POSIX API and then goes and reads from an S3 supported object store. So we went and we made some changes to S3FS, and we used S3FS so that when it receives a request in POSIX, it receives a read request for a file. We go to the object storage and actually issue multiple get object requests, where the get requests are done in ranges of the object. So if you have an object that's, let's say, 100 megs big, we're going to actually issue 20 requests, each for 5 megs. So we use a feature called range reads, which means you provide a starting and an end offset for your read from the object store. And we do the read request using 20 different connections. And what that allows us to do, if we go and we benchmark that, is reach throughput of around 550 megabytes per second, which was sufficient for our needs. So that's how we went about getting the throughput at a very high level. Now, digging a little bit deeper.
Excuse me, just a quick question. What level do you guarantee everything arrive? And do you worry about out of order arrivals for different pieces?
Absolutely. So this is all managed to us inside the S3FS. You can take a look at, actually, it's open source. I have a link at the end to our changes in it. We issue the reads concurrently using multiple threads. So we have a thread pool. It issues the read, and then we manage it to make sure that we give things in the proper order. This basically talks about how we picked the size of the chunks that we read. So we read in chunks. We receive a request for a file. We go and we break that read request into multiple reads for chunks. We picked a particular size. We picked a size of 52 megabytes in our case. How we picked that size is by doing experimentation on what we observed was the optimum throughput based on the read request size. And what you can see is that somewhere around 30 to maybe 40 megabytes objects request is approximately where the sweet spot starts. We picked 52 because 52 is divisible by 4, which, and this is again a fairly low level, which is just a magical number, which is how our object stores segments. So it's recommended that you read in multiples of 4 megabytes, and we picked 52.
Did you do any analysis to find out why you get accelerated performance when you do several connections? Is it because of fairness, or?
So this has to do with how the object store is designed. The object store is designed for lots of connections coming in, and it's not designed to give one connection the optimum performance that it can. So if you think about this storage is really a cluster. It receives a request. It received the request using REST. It goes into some proxy, and then the proxy takes the request, breaks it into multiple lower-level read requests. Each lower-level read request reads a segment, which is 4 megs. These read requests then goes into, after a whole bunch of additional layers, it goes into what's called the slice store, which is where the data actually resides. It's read these, pass them back, and eventually the user gets them using HTTPS. So there's a long process that you go through here. And the reason why you got it is because the idea is that we enable multiple users to come and connect and get the data, and yet keep the price lower.
If you split the request, would you increase the overhead?
There is a cost to it. The cost to it is that the increase in performance from the user point of view is not 100% linear. We're not seeing a 20 times performance improvement, and the reason why is because there's an additional overhead of then processing all of these different chunks. There's also additional overhead from the point of view of the object storage, who now gets 20 requests. So your load on the object storage is also a little bit higher. Now that translates into a cost. You can actually calculate that cost directly. If you go into, if you look at the IBM Cloud Object Storage, then they give you a cost per request. They actually translate into so many cents per thousands of requests. So it increased your cost. We did the math, and it's not terrible. It's sufficiently manageable that we ended up using this in our service. And you see the same thing if you look at any of our competitors. Amazon also will give you cost per so many thousands of requests. Any more questions before I move on? So this was just showing us how we picked the chunk size. We implemented an in-memory cache. We started using TempFS, where TempFS is an in-memory file system for Linux. We actually found out we were getting slightly better performance using just the kernel pages. So we switched to that. And what you're seeing in front of you is the throughput that we're getting on a cache miss compared to a cache hit for reading single object and multiple objects. For single objects on a cache miss, we're getting a throughput of 554 megabytes per second, as I pointed on, I think, a couple of slides before. We're getting 10 times that when we have a cache hit, that is reading straight from memory. Reading multiple objects, we actually saturate the network. So it reaches 1,000, and that's because that's the saturation point for the network we were using. There's a few limitations here that we're hitting, primarily on the S3FS size, primarily the client side copying, that is copying the data into the client buffers, and there's some additional overheads from the Fuse file system. So one thing that we also struggled with is how to handle small objects. So the overheads for reading smaller objects is actually higher than reading larger objects, just because the cost of reaching the first byte is more pronounced with smaller objects. So we didn't fully solve it here. We basically recommended to our customers to go and combine their data sets, combine multiple records into a single large file, which is actually the best practice for TensorFlow and other machine learning frameworks. So doing that helps us in a number of ways. First of all, it lessens the cost of reading small objects and reaching the first byte. In addition to that, it also really enables us to provide some sort of a read-ahead prefetching. I call that poor man's read-ahead prefetching. If you remember, I told you we're reading in chunks. So when we when we receive a request for data from a file or an object, if the request is just for a portion of that object, we actually go and in the background read the entire object. Because in most of the cases, we find that with machine learning workloads, all your data sits somewhere and you end up using all of it. If you're looking at, again, going back to image recognition type of workloads, you generally have all your pictures. Most of the time, the best practice is to go and combine them all into large single file. You're not going to just look at specific images. You're going to be training on all of them. So by breaking our reads and reading in chunks and doing multiple reads, we're performing sort of a poor man's read ahead. So this is a somewhat lower level diagram of how we ended up implementing this. We implemented this inside IBM's Deep Learning as a Service, DLAS, which is available. It GA'd in I no longer remember if it was December of 2017 or January of 2018, but it GA'd a year ago in the IBM Cloud. You can go and take advantage of it today. I highly recommend it. I actually use it myself for other unrelated projects. And what we implemented there is machine learning workloads running on Kubernetes containers. So that's what you're seeing in the blue box on the top. The container is running the workload itself. For each workload, for each Kubernetes container, we bring up an instance of S3FS, which then mounts the training data and the location for the results from the object storage into the local cache. We take advantage of the in-memory cache. We take advantage of S3FS, which enables us to support applications that use POSIX API and then issue S3 APIs. And we use the multiple connections rather than a single read request to support the throughput that we need. We contributed all of our changes into open source, into 3 different projects actually. The first one is you can actually get all the source code that's running IBM Deep Learning as a Service from GitHub. It's called Fabric for Deep Learning. So you can actually take the same code that we're running today and bring up your own service internally on-prem for running machine learning workloads. We contributed a driver for Kubernetes to bring up the S3FS process and do the mounting. And that's also available in GitHub in a slightly different project. And we contributed enhancements to S3FS itself, which is an open source project, into the S3FS GitHub. And thank you.